Morning. My name is Tobias van Reenen. I'm of the Council for Scientific and Industrial Research. So I'm first going to talk to you about ventilation, and then I might overrun my time by a few minutes. Talk about ventilation, the context of ventilation, environmental controls, shortfalls of ventilation, regulatory context, and how UVGI fits in to cover the gaps from an infection IPC perspective. For IPC, we're primarily concerned about transmission risk and reducing transmission risk in our indoor spaces. So thinking about transmission risks and the components of transmission risk, I just want to walk you through the whole picture, whole network of contributors to transmission risk. So would we agree that two major components which factor into transmission risk are infectious dose and susceptibility? Okay, we're happy. Which one of those would you say is an environmental factor? It's the infectious dose. Okay, so let's expand on that. Contributors to the infectious dose are your viable pathogen concentration and your exposure duration. Correct? I don't think I've missed anything. Which one of those two is an environmental factor? Okay, exposure duration, I would argue, is an administrative element. You can control that with administrative controls. Environmental controls are going to be the pathogen concentration. That's where you call the engineer. And then your environmental pathogen concentration is a function of source strength, airborne viability, and your removal rate, right? Do you agree that removal rate is your environmental contributor there? Your airborne viability is a function of the disease, and the source strength is administrative to a sense. It's the number of people in that space. And there, we've spoken about source strength quite a lot under COVID. In fact, learned quite a lot about controlling source strength by reducing occupants. And all these measures we've seen for COVID apply beautifully for TB as well. We reduce the number of occupants. We change our indoor activity levels. Speech levels matter for COVID and for TB. And we're all very familiar with the application of face masks before COVID, and now I think everyone's learned about it, argued about it quite a lot, and we apply that now. So those administrative controls, our environmental controls are our removal rate, right? You want to improve the removal rate, call an engineer, and he will or she will apply air disinfection systems. That's where the UVGI comes in, for example, or room air cleaners. Quite a lot of talk around room air cleaners and different types of room air cleaners. And then ventilation systems. Your ventilation systems can be one of two forms. You can have dilution ventilation or flushing ventilation. What we predominantly use in public spaces is dilution ventilation. Flushing ventilation is very often used in specialist environments, clean rooms, theatres, that sort of thing. Okay, so we've drilled down to environmental controls in the big picture. And if we zoom out again, you can see if we focus on ventilation, we're actually only focusing on a very small portion of all our controls. So while I'm an engineer and while my specialty is ventilation, I just want to make sure that when you think about ventilation, you don't lose sight of the big picture. And hopefully that slide will give you a sense of that big picture. Ventilation is a small part, and it cannot do everything. It cannot carry all the weight that we often put on it. All of these other controls need to be in place. And then something I always have got to put in right up front is air conditioning is not the same as ventilation. I don't have to say this as often as I used to. We've all learned a lot about ventilation during COVID, but it's still an essential component. But from time to time, we still hear a little bit of confusion about the difference between air conditioning and ventilation. And some of the confusion comes from the acronym HVAC, which stands for heating, ventilation, and air conditioning. Now, unfortunately, that acronym bundles air conditioning and ventilation together, and that's why we tend to think of them as the same thing. They're not. HVAC is actually typically three discrete components to achieve indoor environmental quality. So ventilation is defined as the process of supplying air to or removing air from a space for the purposes of selectively controlling your air contaminant levels, primarily. So that's your air purity in indoor space. And it can sometimes, under certain conditions and environments, control humidity and temperature, but it's not its primary function. So ventilation is for controlling air contaminant levels, while air conditioning is a process for controlling the temperature, and then temperature and humidity, and sometimes the purity of the air. So as a rule, air conditioning does very little or nothing for our indoor air quality, contaminant levels, and ventilation is well, the opposite. So we're concerned about ventilation. It is the supply of fresh air to a room for diluting and flushing airborne contaminants. And I often use this illustration. And apologies to the coffee lovers in the room, because in this context, coffee is the contaminant and milk is the dilutant. But if you look at the two on your left, the two coffee cups on your left, look at the rate of coffee production in that room, the glass, versus the rate of fresh air production, the milk. You get a more dilute condition. If you've got a higher rate of contaminant production to the dilutant, your fresh air, you get a higher concentration. If you like coffee, you like the stronger stuff, so maybe not a very good example. But for TB, we want to make sure that that rate of production of the contaminants as a ratio to the rate of production or the rate of fresh air in that room, that ratio is as high as possible. Unfortunately, we can't remove all the contaminants. I mean, if there were no people in the room, then we'd have no contaminants, but we'd have no problem. We wouldn't need to ventilate either. So we've always got this residual contaminant level in the room. Typically, the WHO, the CDC, American Institute of Architects, our national building regulations, many sources prescribe 12 air changes per hour for airborne precaution rooms, airborne isolation rooms. And that's very often considered to be sufficient ventilation. I'd like to show you why that's problematic. Ventilation, your indoor contaminant concentration, the function of the rates, I've already said, at which room contaminants are generated and removed from the room. And what you'll see in those two graphs, what I'm trying to show you there is that as you increase the ventilation rate, I mean, those graphs go right up to 20 air changes, there's always some residual risk, some residual contaminant level. No matter how much you ventilate, there's always some risk. Your risk never goes down to zero. Your rooms are never safe. You've all, by this stage, I'm sure, come across the probability of infection equation. This is it. The probability of infection is the number of new cases over the number of susceptibles. Wells Riley interprets it as this. I'm not going to go into the maths. Just to say it can be estimated or determined if you've got some of those factors. Ones we're concerned about there primarily is T, above the line there. That's the amount of time of exposure. And you'll see a QOA, that's your ventilation rate. There's also factors in there for the numbers of people and so on. That can be rewritten as that equation. Apologies. It can be written as that equation. That's if I've got all sorts of other factors. If I know exactly how much risk I can tolerate in that space. If I know how many people there are. If I know what my ventilation effectiveness is. And they have some idea about disease transmissibility and so on. I can write it like that, and I can do some fancy calculations. So from that, we can calculate a required ventilation rate equivalent to the transmission rate that's at ROE for any limiting disease transmission rate for any specific disease. So if I say I can tolerate a 1% transmission or 5% transmission, I can put that into ROE. I can disease Q, that Q value, that's a quantum generation rate. I can plug TB in there. I can plug different types of, or different strains of TB with and without treatment, COVID, etc. I can put the number of occupants, size of the room, exposure time. If it's a waiting room of 4 hours, we can plug that in there. Just a quick question to the room. What would you say is, what type of environments in our healthcare spaces are at the highest risk or present the highest risk to the occupants in our healthcare facilities? So you often hear waiting rooms. You hear waiting rooms, a lot of people in the waiting room. They're generally undiagnosed. They're probably not on treatment yet. That's why they're coming into the facility for the first time. So let's use that as an example use that equation to figure out how much ventilation we need for a waiting room. So a 100-person waiting room is a reasonable size. It's quite big. Using all the values we've got there for laryngeal TB, adults, 100 adults in the room, plug that through that equation, we come out with a ventilation rate required for a 100-person waiting room of 3,200 liters per second. That is a lot of air. I'll explain to you now how much that is in context. We can apply different technologies, environmental controls, to achieve that removal rate that we need. We can use mechanical ventilation, natural ventilation, or various types of room air cleaners. I'm lumping UVGI into a category of room air cleaners. You get room air cleaners that do particle removal, that's these boxes with filters in them, and then you get room air cleaners that do pollutant destruction. And you get portable room air cleaners and static room air cleaners and so on. And after this, we'll show you a static upper room UVGI. So I don't know if we've agreed. I was hoping that we came to an agreement that waiting rooms are very high risk. However, dilution ventilation alone cannot protect against long-term exposure. You remember that, you might have noticed in that formula, I did try and point it out, there's a little t, that's the hours of exposure. And also our tolerance for risk for the general population using a facility versus the healthcare workers based on regulations amongst one thing and others. The tolerance for risk for healthcare workers is much lower than for users of that facility, and the exposure time is much more. So using that same equation to work out how much ventilation we need to protect the healthcare workers in a space like that, it doesn't come out at 3,200 liters per second. It's 26 million liters per second. So the numbers are bonkers, okay? So that's to protect a healthcare worker from a lifetime of exposure, a working lifetime of exposure. So the question, how much ventilation is enough? It's never enough. Okay. If we were ventilating at 2 million air changes per hour, that's what our healthcare facilities would look like. Okay. We can't do it. We can't afford it. We probably shouldn't do it, even try. For a waiting room, again, not the tornado, but for a waiting room, 3,200 liters per second comes out at about 32 liters per second per person, which is a lot more than the 7.5 or 10 that we read in some guidelines. It's a lot of air. That's what the air handling unit looks like to give us that much air. Okay, it's a big boy. That's the kind of air handling unit that you use in typically laminar flow theatre suites. It will require 145 kilowatts of cooling, about 5 kilowatts for fan power. That would give you, I'm not going to go into the maths of it, but about 75 kilowatts total electrical. For those that work in horsepower, that's what 100 horses looks like. Okay, it's a massive amount of power, a lot of energy, big capital cost to ventilate these waiting rooms using mechanical ventilation. As I said, it's about the airflow we use for 2 laminar flow theatre suites, complete suites. And we know from facility development, our theatres are one of the most expensive places in our hospitals. And now we're being told that we need to ventilate our waiting rooms the same way. You can do it with room air cleaners. Quickly, that's a room air cleaner. I wish I'd included the picture of the room air cleaner in the hotel that we were at. It was a little box, about smaller than a shoebox. Okay, this is a big one. This thing stands about this big. Using the capacity of that one and the 3,200 liters per second, we need 28 units for a 100-person waiting room. So it doesn't look like that anymore. It now looks like that. Okay. A system like that with 28 of those guys is going to cost you nearly 300,000 Rand, excluding running costs, which would be about 30,000 Rand per annum. And they're noisy. This is going to run at 50 dBA each, 28 times 50 dBA. I can't do the math. It's logarithmic acoustics stuff. Call my wife in. I don't know how to do that. It's a lot of noise. You're not going to be able to hear yourself think in that room. And 7 kilowatts of power. Okay, so these kind of things don't help for congregate settings. They're not appropriate. What about natural ventilation? We tout natural ventilation a lot. It has a lot of benefits. It's the highest potential ventilation rate. 15 to 100 air changes per hour is typical. You have a greater perception of comfort with lower comfort expectations. It's a bit of a strange phenomenon. People are more comfortable in naturally ventilated spaces because they don't expect to be as comfortable. You've got potentially better air quality. You've got lowest running costs, in some cases no running costs. You've got healthier and greener buildings. However, when the system fails, when the windows are closed, if the wind's not blowing at all, you've got potentially the lowest ventilation rates because of the variability in performance. Your comfort levels are not guaranteed. You've got also potentially poor air quality if no air moving. If you've got a lot of outdoor pollution, soot, traffic, even noise pollution, dust, they can get into your building. We've spoken about noise already. You've got to consider internal acoustic considerations like ambient noise and wind and speech transmission and so on in the space. So the design becomes very quickly quite technical and difficult to do. Not something that you should be attempting without a suitably qualified and competent engineer. I love architects. Some of my best friends are architects. In fact, I married one. But it's a highly technical design, and the wind can't read an architect's drawings. So you need to actually do a proper design of these systems to make sure that the physics work. Okay. But let's just use a back of the cigarette box ventilation calculation for natural ventilation. The building regulations in South Africa say that our windows must be greater than or equal to 5% of the floor area. So for that same 100-person waiting room, that gives us that many square meters of wall area for a single wall. Assuming a light breeze, I'm from Pretoria, a very windstill part of the country. On a quiet day when you can't see the trees moving, it's about 1 to 2 meters per second. It's a very, very light breeze. In those conditions, through that window, we come out at about 2,438 liters per second for that waiting room. Single-sided ventilation, poorly designed space, minimum conditions, not an optimal design. We're very close to the 3,200, okay? But on a good day, we're not there yet. We need some supplementary systems. Okay. There's some natural ventilation rules of thumb. So any architects in the room and mechanical engineers know that the building regulations are imminently changing, and I have been saying this for about 4 months now. There's a new compulsory standard in the mix, and these are some of the guidelines out of that compulsory standard. So the natural ventilation apertures or openings must be controllable, and that's largely to do with the psychology of naturally ventilated spaces. People, if they can't control a ventilation opening, they will block it permanently. If they can control it, when conditions aren't favorable, they'll close it, but at least you'll still be able to open it when you need it at some time. So please make sure that your naturally ventilation openings are controllable to some measure. Otherwise, people are going to override those measures and you end up with no ventilation. There's some requirements, rules of thumb for room dimensions. Your depth of the room is not allowed to exceed 2.5 times the height of the room. Otherwise, you need to have double-sided ventilation, which gives you 13.5 meters for a cross-ventilated room, which is not a lot, but that's what we need. That's how we need to design our spaces for well-performing naturally ventilated. And I am English speaking, naturally ventilated spaces. So for rooms exceeding 3.5 meters, you need to split your ventilation apertures into an upper and lower opening across the neutral pressure plane. Just some guidelines. Things you'll start seeing in new buildings in the years to come. High volumes, you can have apertures above and below. The rooms are going to be narrow with cross ventilation and maybe higher ceilings even, so that we can get deeper rooms for more people. But we've still got that shortfall. How much was the shortfall? Do we remember? About 800 liters per second. So we need to put something in there. For the days the ventilation system is not working well, or our natural ventilation system is not working, UVGI is a good candidate. You must have all heard a UVGI talk by now, so I'm going to rush through this, and I think I'm just about out of time anyway.
No, keep going.
Okay. All right, so UV is spectrum within the electromagnetic wavelength, little subspectrum. You can see it over there. UVC is between 100 and 280 nanometers. When we speak about UV today, we still largely talk about 254 nanometers, and that's just what the cheapest lamps give us. The emerging technology is 222 nanometer, and some of the UV LEDs, which I think are still quite expensive, can tune those wavelengths to give us greater efficiencies at quite a cost. So UVC radiation has a germicidal effect. It's referred to as ultraviolet germicidal radiation, so you might have heard UVGI. There are some quarters that don't like the irradiation term in UVGI, so they talk about UVG. But I mean, the light in this room is irradiation. It's the same stuff. It's just a different frequency. What it does is, on a DNA strand, your incoming UVGA photon just knocks out some of the DNA, damages. I'm an engineer, so apologies to all the doctors in the room. It damages the DNA so that virus, bacteria, whatever's being affected, can't replicate. It doesn't necessarily kill it, but it prevents it from replicating. So it doesn't kill the bug, it inactivates the bug. Trials done in South Africa, seminal trials, I think, a very important study, shows that an 80% reduction in transmission risk is possible. That is equivalent to about 24 air changes in that study. So therefore, upper room UVGI may be an important addition to IPC. And I spoke about 254 nanometer very briefly, and I spoke about 222. This study was upper room UVGI, which is 254 nanometer. The device we've got in the back of the room is a 254 nanometer. It has some inherent risks, which is why we keep that UV out of the occupied zone and in the upper room. So when we talk about upper room UV, it's that. Emerging technology on 222 nanometer is much safer for our human exposure, specifically for our eyes. So we are likely to see UV systems which flood the entire room in coming years. But here we're talking about upper room because those systems I don't believe are proven yet. That's still something that needs to be done. That study that was done presented some dosing guidelines, which are widely used now, but the consensus has not been achieved on the dosing metrics and the levels which I said reputable, apologies. It should be repeatable, not reputable, which achieve repeatable, effective, and safe system performance. Prescribed dosing levels are volumetric, so we apply a certain amount of UV energy into a room as a function of the volume of that room. Current recommendations are about 14 milliwatts per cubic meter, up and down, depending on who you speak to. Comes out at about 14 milliwatts per cubic meter. Locally, we are considering interpreting that as a per square meter dosing requirement. It comes out at about 4.2 milliwatts per square meter. Yeah, that's floor area. One of the problems with the 14 milliwatts per cubic meter is for high volume spaces, which a lot of our waiting rooms are, you end up with an incredible amount of UV energy in that space. And then it becomes quite difficult to dose that room, I'm going to use the word safely, because the amount of irradiation in the space is then more likely to cause eye irritation. Whereas if you dose at a per square meter criteria, we're not dosing the upper room, the high volume of the upper room as much, and there's some complexity around why not. But we can keep those UV volumes, UV levels down to more acceptable and safer levels within the room without affecting the performance of the system. More work has been done by a number of committees locally and internationally to develop a more appropriate ventilation equivalent performance criteria. So, we've spoken about liters per second, air changes per hour, liters per second per person for ventilation. And then we say there's a shortfall in liters per second. What was it, Gregors? Thank you, Gregor. There's a shortfall of 800 liters per second. How do we apply that using UV? Very difficult, because now we've got two different metrics that don't speak the same language. So we're trying to develop metrics and performance criteria for UV that says this device is equivalent to so many liters per second. I know this device can do 400 liters per second. I'm short by 800. Let's put 2 in the room. Done. So there's a bit of work to do before you can get there. But this would permit ventilation-based additive design, which the new regulations that I've spoken about, which are emerging, have been written preemptively, so that when this is in place, it falls within what we're allowed to do within the regulations. The National Institute of Occupational Health has already built a laboratory to develop this equivalent CADR, clean air delivery rate assessment capability, and a supporting SABS standard is also in development. UVGI should include system planning, space evaluation, looking at room dimensions, occupancy levels, existing ventilation and air mixing, evaluating interference and obstructions. When we do this room, you've got to consider these pillars and things in the ceiling and so on. You should have a design, formal design review process. Otherwise, you're just buying something from someone off the shelf and you've got no comeback. And then you need some control of your design and your commissioning documents. So like a ventilation system, your UV system should be follow the same design and commissioning and installation and setting to work requirements, which are actually prescribed in the building regulations. And then there are factors influencing effectiveness, interactions with ventilation, air mixing, whether or not you do have air mixing, humidities, temperatures, and so on. We'll talk about that a little bit later. And there are a number of guidelines, nationally and internationally. I'll just point you to some of the local ones. To facilitate the proper use of UVGI, the following documents, another typo, apologies for that, have been developed. In existence, there's a SATS 1706, a South African technical standard. It was drafted in 2016. It is under review. That document is coupled with the South African Bureau of Standards Recommended Practice Guide, ARP 0110, which is available to download. It was also drafted at the same time, 2016, and it's the installation and maintenance of guideline for the installation and maintenance of luminaires for ultraviolet germicidal irradiation. So standards do exist. They're not perfect. They were drafted in, I hesitate to say, a bit of a rush, and they are under review because we've done a lot of learning in the last 5 years. So they are under review. Those two standards will be replaced with a SANS 2083, parts 1, 2, and 3. Part 1 is device performance. Part 2 is installation and maintenance. And part 3 will talk specifically about this ventilation equivalence testing characterization, if we can ever get that finished. Then there's also a wiki page, which the CSR has, with others, put up. It's called the Hillside. The hillside.info is the URL, you can find it. The Hillside stands for Healthcare Infrastructure Living Library. I can't remember what the side, it was a bit of a stretch of an acronym. You'll find lots of information about healthcare infrastructure design. There's a ventilation guide, there's gas, there's water, there's a air disinfection page there, which is a summary of a guideline that we developed some time ago. If you want to know about some nuances and aspects of UVGI, you can find that there. That is a wiki. And so the invitation exists for everybody with an interest to get involved in the development of that document. The idea is that we use that as a repository for the best thinking locally on UVGI. Once we've got good information from that page, this can then be brought into policies and guidelines and standards and regulation. Okay, I did mention the regulatory context. The current building regulations do not make provision as they stand. There's National Building Regulations Part O, lighting and ventilation. The ventilation regulation refers to the 10-400 Part O, which is the compulsory standard, and that compulsory standard does not make provision for supplementary primary ventilation. So where it says you must do 6 air changes or 10 air changes or 12 air changes, that's it. You've got to provide that ventilation rate. No supplementary systems may be considered to be part of that 12 air changes. So you can't do 6 air changes mechanically ventilated and 12 air changes with a UVGI system. Not allowed. And that room air shall always comprise only, not comprise only treated and reused air. So ventilation is always required. You can't throw away your ventilation and replace it with UVGI. It's not an option. If your ventilation system doesn't work, or if you have no ventilation, you do not have the option of only installing UVGI. Okay. UVGI does not replace ventilation, it adds to ventilation. Okay. If you've got no ventilation in your facility, I'm going to repeat myself, if you've got no ventilation in your facility or in a space, UVGI doesn't solve your problem. You're still non-compliant. You have to first provide ventilation, and then if you've got budgetary concerns or performance concerns, you can add ventilation to improve the performance of your system. However, currently, to meet the regulation requirements, you have to do that all with ventilation. Anything you do with UV is over and above. The emerging regulations now will make allowance for a supplementary baseline ventilation, a minimum amount of the air changes must be mechanically ventilated, but for instance 2 air changes, and then you can make up the rest, up to 10 air changes or whatever with UVGI. Is that clear? Okay. So we're trying to be progressive with the regulations to allow for these kinds of technologies and emerging systems. And you're going to see this slide a lot. And apologies, there is a newer, there are better studies than this one. This is the one I had. So your IPC does not end with your environmental controls. Ventilation is important to control airborne transmission. It's considered the gold standard. But it's often not the panacea promised. You saw that you need 24 million air changes, whatever it was, to protect healthcare workers. Whereas if you read some of the guidelines, they say 12 air changes is enough. If you actually go do the math, it's far from enough. So it's often not the panacea promised. And higher rates are very often required than what are actually feasible. So we need to think about supplementary systems and other control measures. Remember that ventilation was just a very small corner of that entire picture that I showed you. It was on this side, on your side. It's just a very small portion. We've got to get it right, but it's not the whole picture. 12 air changes may not be sufficient. I'm going to put my neck out and say for congregate spaces, 12 air changes is not sufficient, not may not be sufficient. And a combination of controls is greater than the sum of the parts. And what you'll see in this slide is a sensitivity analysis of this was for measles. Some studies have been done for TB, but they show the same picture, with the exception of the surgical masks, which in this study I believe is wrong. The sensitivity analysis is the uncontrolled ratio, with 100% down to whatever, 0%. So no controls, you've got 100% risk. Surgical masks, according to this study, had very little impact, but we know, I think that this study was considering, in their modeling, was considering surgical masks as a personal protective measure, not a source control. If you consider it a source control, that number should change. See that ventilation in this context with a disease like measles has very little impact because of that rate of production. That contamination generation is so high that even 15 air changes just makes a small change. UVGI, slightly better, but if you can just do some mental maths on that image and you'll see that the sum of the controls is greater than the individual controls. So don't think that just that UVGI or just 15 air changes is going to do the job for you. You need to have everything in place, all your administrative, all your environmental controls to get that effect. Thank you.